In this video, I wanted to talk about power screws. So a power screw would be something like a scissor jack that you'd find like in the trunk of your car. Basically, they are designed to either raise or lower a load. So in the PE handbook, if you search for power screws, that's good. There's a whole section on them. And so there's a couple equations there. The first one is the torque required for raising the load. So T sub R, that's going to be F, which is the load, which will usually give you like a weight or something. And it's times this dm here, which is the mean diameter of the screw. And then divided by 2, and then that's going to be multiplied by L, which is the lead. And that's like how far the screw advances per rotation. And then it's going to be plus pi times mu, which is the coefficient of friction in the threads, times d sub m again, divided by pi times d sub m minus mu L, and plus F times mu sub C. This is the coefficient of friction at the collar, so like where the screw makes contact with like a raising a plate or something. Then times the diameter of the collar, divided by 2. This diameter of the collar it should be given to you, is kind of a analytically derived, because it's not the actual size of the contact area, it's how far that load is dispersed. Would be the best way that I would describe that. Then we have another equation for lowering a load, T sub L, which is force times the mean diameter of the screw times pi mu d sub m minus L, divided by pi times d sub m plus mu L, and plus, or the same thing as up here. And then, so these are kind of the two main equations. It's the torque input required to raise a load and to lower the load. There's a couple of other properties of power screws that it might ask for. So efficiency is going to be the force times the lead divided by 2 pi times the torque required to raise a load. And then there is a property of screws called self-locking that they can have. And in order for that to be true, you have to have one of these two relationships here, which are pi times mu times d sub m has to be greater than L, or mu greater than the tangent of lambda. And lambda here is the pitch angle, which you would probably give that to you as well. So for this L here, L equals the number of starts times the pitch of the screw. So if you have a multi-start screw, even though your pitch might be, 0.2 inches, it's actually going to travel twice that far per rotation. So that's why you multiply by the number of starts. So it'd be 2 times 0.2 or whatever your pitch is. Okay, so I have a pressure problem here I want to run through. So we have a square thread power screw is used to raise a load of 8,000 pounds. The screw has the following properties. And then we have a big list here. And then we're asked to find the torque required to raise a load, the torque required to lower the load, the efficiency while raising the load, and whether the screw is self-locking. So before we get started, just kind of as a sort of spot check, the torque required to raise a load is pretty much always going to be greater than the torque required to lower the load, because you have gravity helping you lower it. So just keep that in mind when you're solving, if you have to solve something like this. So our equation for raising the load, let me write that real quick. these equations are pretty long. Sometimes it might tell you that you can ignore the second part of the equation, this collar friction part. So sometimes you might not have to use that, but we will have to use it in this because we are given information about that up here, this mu sub c, as well as that collar diameter. So go ahead and plug everything in here. So our force is going to be 8,000 pounds. Our mean diameter of the screw is 2 inches. Now L, so we have a single start screw. That's part of the properties. So I know that my L is just going to be equal to my pitch. Because remember, L is the number of starts times your pitch. So in this case, it would just be 1 times 0.4 inches, which is 0.4 inches. And plus pi times mu, which is 0.1 times 2 inches. Okay, and then we're going to add to that our collar friction portion, which is 8,000 pounds, times mu sub c, which is 0.15, and then the diameter of our collar is 3.5 inches. Divide that by 2. Okay, so my inches on this portion right here are all going to cancel out. So I'm going to be left with pound inches and pound inches, which are units of torque. So I think my unit should be good. Let's go ahead and plug this in. So it's going to be 3,417.68 inch-pounds. So that is the torque it takes to start to raise this load. So, let's say you have a screw jack, like a scissor screw jack, and you're trying to lift a big truck. That's how much input torque it would take to start lifting that truck if the screw had these properties. So then for part B, I'm going to write this equation out real quick. Okay, so now we can go ahead and plug things in. So we have 8,000 pounds times 2 inches divided by 2 times pi times my mu was 0.1 times 2 inches minus 0.4 inches for the lead divided by pi times 2 inches plus 0.1 times 0.4 inches. And then we're going to have the exact same collar friction portion as above. So this is just going to be 8,000 pounds times 0.15 times 3.5 inches divided by 2. Okay, so the torque required to lower the load is going to be 2,388.87 inch-pounds. And if we remember from before, we would have expected this one to be lower because you have gravity helping you basically push that screw down. Okay, so now we'll ask for the efficiency. So the efficiency is going to be the load times the lead over 2 pi times the torque required to raise the load. So 8,000 pounds times 0.4 inches divided by 2 pi times 3,417.68 inch-pounds. So my units are all going to cancel out, which I would expect since we're solving for efficiency. So that's going to come to 0.149 or 14.9%. Okay, and then the last thing we're asked for is whether it is self-locking. So remember, we had two equations for this. We had pi times mu times dm has to be greater than L, or mu greater than tangent of lambda. We are not given lambda, and so I'm going to go ahead and use this first equation here. So pi times 0.1 times 2 inches has to be greater than 0.4 inches. So we get 0.63 is greater than 0.4. This is true, and so what that means is that yes, it's self-locking. And what that basically means is once you raise a load, the screw isn't going to back out on its own. You're going to have to apply a torque to lower it. But yeah, these problems aren't too bad. There's only 4 equations here. And another way of writing lambda actually is it's the arctangent of L over pi dm. So I guess that's another equation. That's not, it is listed out in the book, but it's like a sub. It's like how it ties into a previous equation. But yeah, these shouldn't be too bad on the test. It will generally give you almost all the information you'll need, and you just kind of plug and chug. But yeah, I hope this helps.